All right, I certainly hope you took the time to click on the simulation video that I had linked for you, as well as if you wanted to play around with that applet a little bit so you can see what's going on. I realize the applet goes up to just a sample size of 25. That doesn't perfectly fit the central limit theorem in terms of needing a sample size of 30 or more, but you can see at 25, the distribution again is relatively normal. But just again, keep in mind 30 is the minimum sample size to make sure that when you take samples from any population, the distribution of the sample means will be normally distributed. So based on that, let's look at some problems here, okay? So in this case, we know that the mean HDL cholesterol level of 20-somethings has a mean of 53. And here it's saying serum HDL cholesterol is normally distributed, so we know it's normal. And we've got the standard deviation of 13.4. So based on that, let's answer some questions, all right? So first, describe the shape of the distribution of X bar. Well, X bar is going to be normally distributed with the mean equal to 53, because remember that the mean of the X bar distribution is the same as the mean of the population. And the standard deviation is going to be 13.4 divided by the square root of n, whatever n happens to be, based on our sample size. Okay, we don't know a sample size yet, but again, that is because the population is normally distributed. So we know the X bar distribution will also be normally distributed. All right, so moving on to the next question. What is the probability that a randomly selected 20 to 29-year-old has an HDL above 60? Okay, this is one randomly selected person. So this is actually what we did in the last section. We're talking about one single person. And so we would like to find the probability that that single person has an HDL greater than 60. So we're going to use our normal CDF function because we know it's a normal population. Our lower boundary there is 60, up to whatever. So again, no boundary, so 1E99 with a mean of 53 and a standard deviation of 13.4. Again, that comes from section 6.3. This is the type of problem we did in the last lesson. Whenever you type that into your calculator, you should get a probability of 0.3007. Okay. All right, moving on to the next one. What's the probability in a random sample of 15 people? Okay, so now again, we're going to take groups of 15 and find their average, okay, find their mean. And so we want to know what is the likelihood we grab 15 people and we find their average HDL, and that average is above 60. So now, instead of wanting the probability that X is greater than 60, we want the probability that X bar is greater than or equal to 60, the mean of all 15 of those people that we are sampling. So we know, because our population was normal, that our sample is going to be normally distributed. So we can still use normal CDF. Our lower boundary is 60. Our upper boundary is non-existent, so the 1E99 just keeps going on and on, okay? Doesn't end. Mean is 53. But now our standard deviation is 13.4 divided by the square root of our sample size, which in this case is 15. Okay, when you type that into your calculator, you can type 13.4 divided by square root 15, like right into the prompt screen or right into after the comma. Just do 13.4 divided by root 15. Call it good, okay? It won't be a problem. Your calculator knows how to handle that. Please double check and make sure you get 0.0215 whenever you do that calculation, okay? All right, so the next one, what's the probability in a random sample of 20 people the average is above 60? So again, same thing we just did. We're looking for the probability that the mean x bar is above 60. We know that our distribution of sample means will be normal with a mean, sorry, I'm writing all of these wrong. I'm just realizing, oh, sorry, no, I'm good. Lower bound, 60. No upper bound, so 1E99. Mean, that's what I was trying to get to, 53. But now our standard deviation is 13.4 divided by 20 because our sample size is 20. And this time we will find the probability is 0.0097. All right, so as you may have noticed, as we went from a sample size of 1 to 15 to 20, our probability was doing some changing. We went from 0.3 to 0.02 down to 0.0097. So our probability is going to be getting smaller, okay? And that's one of the things we're going to focus on here. So as n increases, the probability decreases, okay? And I said, let's explain this from two different perspectives, common sense and mathematical. So from a common sense perspective, okay, let's think about that one, okay? It would not be hard to find one person with an HDL of 60, okay? With an HDL of 60 or more for that matter, okay? So an HDL of 60. But to find a group of 15 people with an average HDL greater than or equal to 60 would be more difficult. Okay, so again, to find one, not so hard. Okay, to find one person that's over 6 feet 6 inches tall, maybe not that hard. To find a group of 15 whose average height would be over 6 feet 6 inches tall, a much more difficult task. And then make that group bigger. What if I need to find 20 people with an average of more than this? 30 people, 40 people. It gets harder and harder and harder and harder. So as your group gets bigger and bigger and bigger, to get that average is more challenging. Okay, from the mathematical standpoint, since your standard deviation is decreasing, I didn't mean to hit an equal sign there. Since your standard deviation is decreasing, the normal curve gets skinnier and extreme values are even more extreme. Or in other words, rare. And if you watch the simulation, you would notice that that normal curve did get skinnier. They've got the nice big population one, and as you draw more and more people in your sample, that normal curve of the sample means got smaller and smaller and smaller toward the middle. Okay. And so one quick last question here. What might you conclude if a random sample of 20 to 29-year-olds has a mean serum above 60? Well, based on what we found up here, okay, and we're talking about a group of people, it's pretty rare. We're talking about a probability here of 0.0250097. That's what we start to call, again, those unusual observations. So this actually is going to lead us to kind of what's coming up in a subsequent chapter. But what we might decide is if we had a random sample, maybe the assumption that the mean is 53 is incorrect. Okay, maybe something's changed. We don't know what that would be, but maybe we're working with some wrong data. Okay, maybe we're working with some wrong information. And so maybe an assumption about the population is incorrect. And again, that's going to help us kind of foreshadow what's to come.